A single speck of dust drifts through the air, settling against the rough edge of a red clay brick. But this brick isn't sitting on the ground. It is suspended halfway up a 50-story structure, locked in a battle with gravity. To construct a monument that reaches into the sky, humans must first solve a physical impossibility. We cannot step onto thin air to lay the next row of steel or concrete. Before the permanent architecture can exist, engineers must construct an entirely secondary, temporary world. This temporary world operates on a massive scale. It requires rigid standards, precise load-bearing calculations, interconnecting tubular steel, and cantilevered platforms over empty space. This animation maps out the process we call scaffolding. It is a rigid framework of platforms that continuously elevates, assembling itself upwards in exact synchronization with the host building. Scaffolding functions as an engineered battle of physics and geometry against gravity, making the vertical ascent of modern architecture possible. Down at the base of a traditional brick wall, the foundational anatomy of a scaffold begins with two primary elements. Vertical posts, or standards, rise out of the ground, connected by longitudinal horizontal pipes known as ledgers. But the traditional bricklayer's scaffold has a severe structural constraint. It cannot support its own weight. To remain upright, the entire framework must physically lean its weight into the host building. Looking at this diagram, you can see how this connection is made. Transverse horizontal members, labeled putlogs, bridge the gap from the outer ledger and insert into cavities inside the wall. To prevent sideways collapse, diagonal braces are lashed across the standards, locking the grid. When masons and materials load onto the wooden platform, their combined downward weight travels along a precise path. The energy flows through the platform, into the putlogs, and transfers straight into the permanent brickwork. Because of this physical connection, a bricklayer scaffold functions as a temporary extension of the building itself. The framework trades standing on its own for the advantage of climbing rapidly alongside the masonry. When construction shifts from small bricks to massive, impenetrable blocks of solid stone, the physics change. Builders can no longer leave deep putlog holes inside the load-bearing facade. To solve this, engineers developed the mason scaffold. It is a framework completely detached from the wall, designed to carry extreme crushing weight without penetrating the permanent architecture. The top diagram details this independence. Instead of one frame, the structure uses two identical frames of standards and ledgers. One sits against the wall, the other is 1.5 meters away, relying on heavy raking shores to hold the system steady. As commercial building scales expanded, timber limitations became a liability. The industry required materials supporting the demands of high-speed, high-load construction. Tubular steel replaced wood. Instead of relying on rope lashings, builders began using mechanical patent couplets, locking 38mm steel tubes into rigid grids capable of bearing exponential loads. The bottom diagram illustrates the foundation of this modern system. Notice the square base plates welded to the bottom of each vertical standard. These plates take the independent downward force of the steel grid and distribute it safely, ensuring the tubes don't shatter the concrete. This evolution to independent steel framing allowed engineers to safely suspend immense industrial weights in the air while leaving the building's facade untouched. But sometimes, even the most advanced ground-level foundation is impossible to build. In a dense, busy city, placing a scaffold on the pavement would paralyze urban traffic. When the ground is completely off-limits, builders use the needle scaffold. It is a platform that cantilevers directly out from upper-story windows, bypassing the street entirely. This diagram breaks down the needle scaffold. A timber beam, the needle, passes through the wall. Inside, it's clamped by struts to prevent tipping. Outside, an inclined strut manages extreme shear forces, pushing the overhanging weight back into the solid wall. When crews maneuver multi-ton blocks of stone entirely above street level, standard platforms aren't enough. They build wooden gantries. This sketch illustrates a gantry with a traveler. While platform gantries strictly provide a static workspace, this framework is topped with longitudinal runners and steel rails. This allows the heavy lifting tackle to glide, shifting stone blocks parallel and perpendicular to the wall. By manipulating tension, compression, and leverage, Needle and gantry scaffolds allow crews to build an industrial workspace in midair. If you pull back and observe a massive construction site in its entirety, you see all of these systems working in unison. Brick, mason, tubular steel, and cantilevered needle scaffolds interlock to form a single, unified exoskeleton. This heat map visualization reveals the hidden physics of the site. The temporary framework absorbs, deflects, and manages millions of pounds of compressive and tensile force, constantly shielding the fragile new building inside. The scaffolding network requires the same rigorous safety calculations and structural integrity as the permanent skyscraper it surrounds. Once the work is complete, every component is dismantled and removed, leaving the building to stand as if it appeared on its own. The phantom city vanishes, leaving the permanent architecture standing alone. But while we know how to build safely into the sky, what is the engineering solution when the earth beneath a building begins to fail? When the foundation cracks and gravity threatens to pull a structure under, engineers have to dig down. Next time, we go beneath the surface.